today about stability of perturbations in some certain class of massive gravity-inspired theories, which have recently been used in the context of the holographic conductivity. And the main results will be based on this work with Andrei. So yes, I will give a super short introduction for the RGT massive gravity, but since it has reached the 500 limit of the statisticians, just dividing by the people in the room, you all read it at least 10 times. So yes, so what I'm interested in is actually the formulation in the Stuckelberg language, where you just write the potential for the graviton mass in terms of the characteristic polynomial for the square root matrix, and you parameterize the F mu, the reference metric, in terms of these Stuckelberg scalar fields. And what we call a reduced massive gravity, and what is the how we started to think about it, is that we noticed that it's simple observation that you can equivalently write the massive gravity action in terms of the other matrix, IAB. The difference from the usual inverse G times F mu matrix is that you just contract here the spacetime indices and leave the configuration space indices uncontracted. And you can, there are small observations you can make. You will see that they are actually the scalar fields are coupled minimally with gravity. They just have non-standard kinetic terms. They are a bit mixed, but otherwise minimal. And a priori, there is no really limitation on the number of the scalar fields you use. And so we studied the case of two Stuckelberg scalar fields. It's like the simplest, but not so trivial version of the massive gravity. And in this way, you also see how it is useful to use this matrix, because in the case of two fields, it's just a 2 by 2 matrix, and it's much more simple to take the square root in this case. So you can write the characteristic polynomials of the square root matrix in terms of the trace and determinant of the actual matrix, and it just simplifies the computation. And yes, this theory is Lorentz violating in the sense that it admits a Lorentz violating background, and you can choose the directions in which you want to align your scalar fields, and the mass term will arise exactly in this plane. But I will not do cosmology, and I will not therefore also talk about the Lorentz violation so much. Before I start the ADS-CFT part, I have a small remark relating the different dynamical structure in the theory with two Stuckelberg fields, which is that in the RGT, you know that there's that not all the Stuckelberg fields are dynamical, meaning that if you look at the determinant of the kinetic measure, which is just defined as the second order derivative of the Lagrangian with respect to the time derivatives of the fields, then for the RGT it vanishes, whereas it doesn't vanish for in the case where there are only two scalar fields. So in a sense, both of the scalars propagate. But you should not think that it's like that the ghost now is propagating. It's just that the 2 degrees of freedom are there, and then you have to do the analysis. It depends on the.
So the metric on the field space is positive.
Here I haven't even defined it, and it actually depends on the signature also of the reference metric.
Normally you'd expect if it was minus plus, then
yes.
Minus 5 would be plus.
Yes, I can say that if you since we are actually looking at the Euclidean reference metrics, then when you go to unitary gauge and then you do the usual analysis, you look for the Hamiltonian constraint, then the H00 component is not affected, and the Hamiltonian constraint is still you have the Euclidean version, and this problem changes if you take
So why do you need to take a specific structure of the potential in that case?
Sorry?
Why then you can take, you could take any potential?
Yes, you can. And this is actually, this is what other people will do later for the holographic applications, because once they know that there is no really intention, just think whatever you want. So for the holography, we will use the black-line solution, which was found by Weg a couple of years ago, and you include the cosmological constant and the gauge field in the action, and then you use the quantum coordinates, where there is the time direction, radial direction, and transverse directions, and you arrange the Stuckelberg fields in the transverse directions, and take the reference metric to be included, and then on the background solution where the Stuckelberg fields are proportional to the xy coordinates and the Maxwell field has only the temporal component, the theory against the black-line solution where the f of r is, it's like similarly as for the black holes, it has a horizon at the given radius and it asymptotes to the center as r goes to 0. ADS-CP correspondence maybe a bit marginal for the modified gravity workshop, but people do this, and the inspires even run out of these tags which they have for highly cited papers, and they are off by an order of magnitude. This paper is cited 10,000 times, which is quite amazing. So as we all know, the duality between 2+1 dimensional gravitational theory and a d-dimensional, and a d-dimensional quantum field theory, and the core of the correspondence is that the background values of the bulk fields are sources for the operators in the field theory, and like in particular the metric on the boundary is the non-dynamical metric of the field theory, that's valid. And the dynamical fields that we are interested in this context is just the metric and the Maxwell field, which give rise to the stress energy tensor and the current. And ADS-CFT, it arose in the string theory, and so usually I think it's for the small constituent but of the nature, but one has found the applications for condensed matter physics, because you describe them by strongly interacting field theories, and so you can use the duality to learn something more about it. And like the background solutions for the dynamical bulk fields, they give rise to the thermodynamical properties of these systems, and when you go off the background and you look at the perturbations, then it's the domain of the linear response theory, where you relate the perturbations and operator expectation values with the background sources by the retarded Green's function. And when you correctly identify the physical fields on both sides, then you can see that you can calculate the transport properties and the materials, and then particularly look at the electric conductivity, because this calculus is governed by the generalized Ohm's law, and when you identify the electric field in terms of the gauge field and use the above relation, you see find the conductivity in terms of the retarded Green's function. And the Green's function you calculate in ADS-CFT correspondence using their machinery, and one can find that it is just determined by the expansion coefficients of the Maxwell field near the ADS boundary, where the small a is just the perturbation of the Maxwell field, and these are just expansions in terms of radius. So here are the results just for Einstein-Maxwell theory, which you get from ADS-CFT result, when you compute the real and imaginary part of the conductivity as a function of frequency, and these are the experimental results for 2+1 dimensional graphene, and they are somewhat similar, and there are characteristic features. The real parts tend to constant as one approaches large frequencies, and there is this drop off of the of the conductivity at some point given by the chemical potential. And what is different is this part here, that in real systems the conductivity starts to grow again for small frequencies, whereas here in ADS-CFT result, actually one doesn't see it, but there is a delta function. You cannot see it numerically, but you can see that the imaginary part diverges and has a pole, so you conclude that there is a delta function. And this is due to the translational symmetry, because if you just do the ADS-CFT, you get a translational invariant field theory where you cannot really describe the dissipation of the moment or momenta, whereas in real systems there is the lattice and impurities, and therefore the results are finite. So in order to correctly do the moment, to describe the transfer properties via ADS-CFT, you need to incorporate the effects of the broken translational invariant. And translational invariance on the QFT side follows from the diffeomorphism invariance of the bulk gravity theory. And so what you can do, you can write the diffeomorphisms, and in this sense, David Wade came up with the idea that one can use massive gravity, which in the unitary gauge does break the diffeomorphism. And indeed, we will see on the next slide that it renders the conductivity finite, and one can use such an approach to describe the momentum properties. What is interesting, one can also sort of write we modified the conservation laws for the energy momentum tensor, for the field theory and energy momentum tensor, in order to somehow describe this momentum dissipation. And so it has been postulated by its phenomenological model. There's this person who postulated that you can describe this momentum dissipation by introducing modified conservation laws, where the energy density is conserved, whereas the momentum is being dissipated on some characteristic time scale. And by using the analysis of the dispersion relations of the shear diffusion mode, you can in hydrodynamics, you can see that this this law changes the dispersion relation in such a way that the decay rate of the shear diffusion mode gets additional contribution and is dissipated. And you can also find this time scale by just looking at the poles of the Green's function and from the holographic theory, and you can find the stability condition. Because it has to be positive, otherwise the momentum will be, there will be a gain in the momentum instead of the dissipation. So the dynamics which are related to this electric transport lies in the vector sector of the theory, which in this theory are just the metric components, the Maxwell components, Schucker-Berg components. And the previous results were obtained in the unitary gauge because it's easier to make it in the unitary gauge. But a part of our work was to repeat the analysis in the gauge-invariant way, mostly because without the deep invariant gravitational theory, it is problematic in ADS-CFT because you cannot produce the full dictionary, you cannot define the field theory stress energy tensor, you cannot find the counter terms which removes the divergences and so on. And so we rewrote the theory in a gauge-invariant way by introducing these sets of variables plus the Maxwell field, which is gauge-invariant. And you see that only the two of the vector fields remain, and they are defined that it's big them to the Maxwell field and this phi r, because they are directly related to the ones in the unitary gauge. So there's actually independent the unitary gauge. It is exactly the same as the gauge-invariant results. And these are the results for the conductivity. So you see that the real part now has a peak. I haven't plotted the other part, but it has a peak and it's finite. And also the imaginary part doesn't diverge anymore. So it is indeed a way how to obtain a finite conductivity. And so the last thing, we actually want, which is actually the main thing, we wanted to see whether we can get the stability condition which they got from these phenomenological laws just by doing a perturbation analysis for the massive gravity part. And I mean, what we did, we just looked at the gauge-invariant quadratic action for the vectors. And I mean, it was a bit technically difficult, and we got all the terms, and it was dependent on all the fields, and we had to impose this constraint because that's how the definitions of these pi r and pi t's are. And but when you introduce the Lagrange multiplier, you can actually resolve the Lagrangian to obtain a nice quadratic Lagrangian, where you can see the kinetic terms here. And one actually can see that in order to avoid the ghost, you do need this stability condition, this mass, which is this combination of the betas 1 and betas 2 of the scalar fields, that it has to be finite. So it was at all r's. And yeah, so these are my conclusions. So the massive gravity in the two-dimensional fields can be used for describing the transfer properties in holographic approach. And so I don't know, when everyone will be done with all the high gravity branches of the solutions, maybe you want to know this. And we did all the analysis, so we found actually there are 6 degrees of freedom, which are propagating. I didn't tell about the tensor modes, but there are 2 tensor modes which are massive, and the 2 vector modes due to the Stuttgart fields, and there are 2 vector modes due to the massive. And there is a stable region in the parameter space by these conditions on the parameters, and either one is for the negative and the two has to satisfy this relation. That's all. Thank you.